So in the previous lecture, I showed you how to solve the minimal surface equation with the Newton method. And what I would like to show you this time is a simpler approach, something that is, let's say, more easily implemented because we don't have to form the derivative of the operator, namely a fixed point iteration or a Picard iteration. And one of the things that I think is worth pointing out is that Newton's method is also a fixed point iteration. In the context of PDEs, when we say fixed point iteration, we have something very specific in mind typically, namely that we split the operator in a way that I'm going to show you in a minute, and then just, let's say, freeze a certain coefficient and solve for the solution again and again and again and again, every time freezing the coefficient on the previous iteration. So there are many different ways how you can define fixed point iterations, and like I say, Newton's method is one. Pseudo time stepping is also a fixed point iteration, but in the context of PDEs, when we talk about this in our community, we typically have something very specific in mind for this. Another word that you will often hear in this context is Picard iteration, which is also just freezing the coefficient, solving for it. So what I would like to show you then is how we solve the minimal surface equation with this particular method. And just to remind you, the problem that we would like to solve is minus divergence a divided by the square root term, gradient u. And in the examples that we're going to choose, we're going to say a equals 1. Now, the concrete problem that I want to solve in this lecture, because it matches the one of step 15 and that we discussed in the previous lecture, is where the domain is the unit disk. The right-hand side is 0, and the boundary values are sine of 2 pi x plus y. What we would like to do is solve this with Picard's iteration. So Picard's iteration basically starts from the following idea. So if I want to solve LU equals F, then I would like to rewrite this nonlinear operator, LU. So you can think of this here. This is LU. Okay, it is an operator that takes a function u, in this case in h1, and maps it to something that is in h minus 1. Okay, so it is something that takes a function u and returns something else. So I would like to rewrite this operator LU in the following form, namely as g of u, that might still be nonlinear, times u. So it is linear in this term here. And then we would like to repeatedly solve the equation g of uk times uk plus 1, or applied to uk plus 1, equals f. In general, this g of u, this whole thing will be a differential operator that acts on uk plus 1. Okay, so it is not just something that acts on this argument u, but it acts on whatever comes after this. And the other important part is that this is a linear problem in uk plus 1. And it needs to be a linear problem because these are the only ones that we can solve, right? We know how to solve linear differential equations. We don't know how to solve nonlinear differential equations, and so the whole purpose of this approach is that we rewrite this whole thing in terms of a linear equation, in terms of a quantity that we would like to compute in every iteration. Okay? Now, in the context of the minimal surface equation, when you want to apply a Picard or fixed point iteration, what that requires us to do is that we solve this problem here iteratively. So if I'm giving you uk, then you can solve for uk plus 1, okay? And then once you have uk plus 1, you stick it back in here and you solve for uk plus 2, and so on and so forth. So we go back and forth between solving for this and then using the solution uk plus 1 as a coefficient for the next iteration. Okay? This is linear in uk plus 1, and let's say if you look at the original equation, you need to compare it with this one here. What we really have done is we have considered this whole thing here as a coefficient, okay? And we freeze this gradient u here that involves the solution that we don't know. We freeze this here at the previous iteration gradient of uk. Okay. That's why I say we consider the operator frozen around or linearized around the previous iterate. So you will ask, well, why do I choose this particular form here for the iteration? I could choose other variations too. Okay, so if I write the previous slide in a different form, I could say that GU is minus divergence A over square root of gradient 1 plus gradient U squared gradient W. W is the argument that I apply to. Okay, so why do I choose this particular form? I could also have chosen this G as LU over U. You remember that I wanted to choose it in such a way that GU applied to U equals LU, right? So if I multiply this with W equals U, I get back LU. So this would work here. But if you look at what that means, I would have to apply this sort of operator here to W over U. Okay, well, it's linear in W. This is all fine. But there are no derivatives on W. And if you think about this, whether this equation has a solution or not is not quite so clear. Okay, because this is just a function here as a function of x. If I give you U, you can compute this whole term here. It's a function of x. So I'm going to have a problem if I say G of UK times UK plus 1 equals F, where the solution UK plus 1 is essentially, I can determine that at every single location. So it's not a differential equation. This may or may not converge. I have a hunch that maybe it does very slowly, but I'm not entirely sure about this. So the point is, I could in principle do this. It's not a differential equation. It is questionable, at least. I could also have chosen it in the following way, where, let's say, instead of freezing the gradient U here, I'm going to, so this is gradient U times gradient U, and here I have another gradient U. I could have frozen it here and once here, and I get something like this. And this is also all nice, but it is not a linear problem in W. So if I want to solve the problem G of UK, UK plus 1 equals F, then it's not linear in UK plus 1. And the whole idea of using this iteration was, of course, that we want to solve a sequence of linear problems because these are the only ones that we know how to solve. Okay, so this does not work. So the general answer to this is that there's an element of experience to how we actually choose this G of U. Sometimes you have options, okay? Sometimes there's a clear answer. So in this particular case, I think there really is only one answer of how you would do it, namely the one that I showed you first. But the whole point, let's say the criteria by which we choose it are that you want that G of U is linear on the argument that you multiply it with, okay? You want the equation to be a well-posed PDE, so GU times W equals F needs to be a well-posed PDE in terms of W. And we want that this operator G of U has a convenient structure. So typically what we want is to mimic, let's say, the Laplace operator or something that we're familiar with, okay? Now, if you look at this again, so here, this is the form that I choose. In terms of UK plus 1, it is a linear operation, okay? It is well posed if this coefficient here stays bounded from below. So if the gradient of UK does not blow up, then this whole thing is a well posed PDE. And if you look at this again, this is a little bit, well, so this is a known function, right? Because I know UK. So this is just a coefficient times the gradient and the divergence of this. If you think about step 6, for example, step 6 solved the problem with a spatially variable coefficient, right? This is spatially variable because this is UK of x. So this is something that we know. This is an operator that we're quite familiar with. It's a little bit like the Poisson equation or the Laplace equation, just with a spatially variable coefficient. So to solve this particular problem, we're quite familiar with. We know how to solve this. We know how to, let's say, choose a linear solver, how to choose a preconditioner, and so on and so forth. So we have chosen this particular form of the Picard iteration because it leads to something that we understand. So the next question you could ask is, okay, so I have this iteration where I'm given uk and I want to compute uk plus 1. Well, so what do I start with? So what is my u0 when I want to compute u1? And I mean, clearly, we expect that this will converge quickly if I can choose u0 to be close to the exact solution. But of course, I don't have the exact solution. So in the current case, it will actually suffice if we just use u0 equals 0. That is a function that does not satisfy the boundary conditions, but that doesn't matter because if I put this in here, I'm going to solve for u1, and u1 enforce to have the right boundary conditions. Okay, so there is no harm done doing it this way. Now, you might say that maybe a better starting guess would be if I choose my u0 to be the solution of the Laplace equation. Okay, so minus divergence a gradient u, so that essentially forgets the nonlinearity here, equals f, and u0 equals the right-hand side. And the answer is yes, yes, this will lead to more rapid convergence, but if you think about it hard enough, if I choose u0 equals 0, then my u1 is going to satisfy what equation? Well, if u0 equals 0, then the gradient of u0 is 0. Okay, so the coefficient is in fact a divided by square root of 1 plus 0 squared. Well, it turns out that u1 actually satisfies exactly the equation that we just talked about. Okay, so in this particular case, if I start from u0 equals 0, the first iteration is already what I just argued would be a better starting point. So starting from u0 equals 0 just leads to one extra iteration compared to starting with this. But of course, this here would have required me to solve a Laplace equation. So in the end, I don't win anything. Okay. So with all of this said, what I'm going to do for the rest of this lecture is that I'm going to try to morph step 6 to do exactly the sort of thing that I just talked about. And of course, as always, I mean, what could possibly go wrong if you want to implement a tutorial program or implement a finite element program in front of a camera? Well, we will see. I mean, it's an interactive demonstration. We'll see if this works out. So what I'm going to do is I'm going to start Eclipse. I'm already in the step 6 directory, so it looks like it always does. I'm going to create an Eclipse project here. So if I say CMake, it tells me all of the generators that I can choose. So I'm going to create an Eclipse project right here. Okay. Dot. Okay. So it has created not just a make file, but also a an Eclipse project. The Step 6 tutorial program has, of course, all of the comments in there. I will get rid of this. So if I say make info, it tells me all of the things that I can do here. So one of the things is make strip comments. I'm going to get rid of the comments because they're just going to obscure what I really want to do. Okay, so here is my Eclipse. I have already opened this. Okay, so this is the version of step 6 without any comments in it now. And what I will do is, I should also say, so last night when I prepared for this, I created this project here and I imported it into Eclipse in the same way as I show in lecture 8.01. So Eclipse already opened the project that I just created, and it shows me the code here. So what I will do is I will just go through step 6, and I assume that you know step 6, and I will morph this in the direction that I want it to go. Okay, so what do I need to add? So instead of just the current solution, I will also have to have the previous solution. Okay, so this will become my UK plus 1, but I also need the previous solution. Okay, so this is my UK. This is going to be the linearization point. Now let's just go through the top from the top to the bottom. So I don't need the coefficient. Okay, it's gone. What I will need here, I also don't need this function here. What I will need is the boundary values coefficient. So let me copy and paste this from the right place. So step 15, step 15.cc. So the place where we define the boundary conditions is right here. So it's just this piece of code. Let's just copy that in here. Okay, so the constructor stays the same, the destructor stays the same, the setup system, I have the current solution. I also need I need to reinitialize the previous solution. Going through the rest of this thing, everything stays the same. Okay, so in assemble system now I need to evaluate the previous solution and use that as the coefficient in the equation. So I'm going to get rid of the coefficient that we previously had in step 6, and I need a vector. So I need to evaluate the solution gradients at the quadrature points. Okay, the gradients are tensor 1, dim objects. Okay, so previous solution gradients, and I need to evaluate this at the individual quadrature points. Okay, I don't need the previous coefficients, but I need to ask the FA values to give me the get function gradients. Eclipse does not want to autocomplete. Previous solution, okay, and I need to put this into previous solution gradients. So at this point now, I have the value. So this is the nodal vector of the previous solution at all of the, let's say, nodes of my mesh. Okay, so it's a global vector, and I compute the gradients here at the quadrature points of the current cell. Okay, so if you look at the equation that I want to solve, right? This is the equation. So there's this coefficient here that I have to evaluate at every quadrature point. A was equals to 1, so I need 1 over square root of 1 plus the previous gradients squared. Okay, so let's put this in here. So instead of the old coefficient here, I'm going to have 1.0 divided by square root 1 plus previous solution gradients Q index times previous solution gradients Q index. Okay, so that looks good to me. Let's make this a little bit smaller here so that we can see it all. Okay, so 1 divided by square root of 1 plus, let's make this a little bit easier to read. Okay, 1 plus the previous, so UK squared, or gradient UK squared, times gradient phi I times gradient phi j times the times jxw. So it's times the dx in the integration. In my case, I don't have any right-hand side. Okay, so I'm going to just remove this here, and the rest of the function remains as it is. The solve function remains as it is. The refine grid function, well, we could copy something like from step 15, where if I do refine the mesh, I'm going to copy the solution from the previous mesh to the current. I'm not going to do this right now. That would be an obvious choice for extension. So then the output results function, I want to output not just for every mesh refinement cycle, but also for every iteration. Okay, iteration. So I'm going to give this another argument, and then I need to change this in the declaration as well. So I go to the function name and I hit F3, and it automatically jumps to the place where it is declared. Okay, copy it here, and then I go back over here. So the file name is going to be solution dash plus utilities int to string cycle plus dot utilities int to string iteration, okay, plus dot, let's say VTU. We'll take VTU format, okay. And instead of just outputting the grid, I actually want to output the whole solution. Data out, attach, DUF handler, no auto-completion, DUF handler, data out dot add data vector solution. I'm going to call it solution. Data out dot build patches, data out dot write VTU, and so I'm going to make it right into my output stream here. Okay, so that's all I need to change here. Now, in the run function already has to cycle over all of the meshes. Okay, and then if I want to iterate, let's say do my fixed point iteration or my Picard iteration on every mesh, starting from a 0 solution. Okay, so you remember the solution is set to 0 in setup system unless I were to import something like we did in step 15. So I'm just going to start from 0 here, and I'm going to do something like an iteration, so a 4 over the iterations, iteration less than, let's say 5 for simplicity, plus plus iteration. And output results, so cycle is the mesh refinement cycle, and then the iteration here. So that's basically all I need to do. There's one step, so after solve, I need, or at the end of this whole thing, I need to, of course, set previous solution equals the current solution. Okay, so I keep replacing my linearization point previous solution by the current solution. Before I do this, one of the things that I think would be worthwhile doing is to output the size of the difference between the two of them, because that's something that we could use for estimating convergence, other than, of course, doing something like in step 15 where I compute the actual residual. So I'm going to define a vector difference that has the same size as the number of degrees of freedom that I have. Okay, I'm going to say difference equals solution, difference minus equals previous solution, and then I'm going to output, let's say UK minus UK minus 1. So that's the norm, the L2 norm of it, and it's difference dot L2 norm and an end line. And what I probably also want to do is somewhere here to say what the number of the iteration is. Iteration. Okay, so that's basically all that I think I need to do. Let's see what else comes down here. I don't need to output the mesh anymore or the solution anymore after this whole thing. And this all looks good to me. So let's just go to the makefile targets. Okay, I'm going to say make all. Down here I'm going to see the progress in the console output, so we will see if I made any mistakes here. Would be a miracle if I didn't. So the obvious targets for improvement in this program that I didn't do now is clearly that it would be worthwhile to take the solution from one mesh to the next and that I would have a better way of estimating convergence. So right now I don't terminate my program at all, other than having a certain number of iterations. I should have saved my program here. So let's try this again. Yeah, so right now if you look at the iteration, it just does 5 iterations on every mesh. What I should be doing, of course, is I should monitor, let's say, the difference between my previous and the current iteration. Or, like in step 15, I might just monitor the residual of the equation. And if that becomes small enough, then I should just terminate the iteration and move on to the next mesh, for example. Or if the next mesh is good enough, then I should terminate the overall iteration. So it ran, and it did not produce an error. That is a miracle. Or it compiled. Let's run this whole thing. Okay. So you see that it, well, okay, so that that does not look like quite right. So it computes a 0 solution. Why is that? That's because I did not imply the boundary values. So we will need to do this now. Okay, so the boundary values in step 6, I need to copy the boundary values. Where does this happen? I think in step 6 we have 0 boundary here, right here. So I need my boundary values. Okay, save, compile. Let's see what happens here. So clearly with 0 boundary values, because I have a 0 right-hand side, the solution will be 0. In that case, there is not very much to do, right? What it will find is that the solution is 0. And then if you have a 0 solution, then clearly the mesh refinement will not do anything at all either. Okay, so it compiled. Let's run it now. Okay, so now it does something. Okay, if I make this larger, what you will see is that the difference goes down. Okay, so there's probably an equal sign missing here if I had been more careful. So the difference becomes smaller in every iteration, so it does indeed converge, if slowly. Okay, so you see that the finer the mesh becomes, the slower it actually, the convergence becomes slower. The first step is always very large, because in the first step my UK minus 1 is just a 0 solution, so it doesn't even satisfy boundary values. It's completely off. But then after the first iteration, so this, after the first iteration, this is my U2 and this is U1. U1 solves the Laplace equation. U2 satisfies the first iteration. Okay, so you see that after that convergence is pretty slow. So let us just look at the visualized solution. So visit. Let's see if this looks like we expect it to. Okay, I'm just going to go straight to the finest mesh. I'm going to say add pseudo color solution. Then maybe I'm going to extrude it into the third direction. Elevate. Okay, draw. So this is how this looks like. This is the first solution. Okay, so this is the solution of the Laplace equation on that mesh. Let me get rid of all of the annotations here to make it clear. Okay, apply, dismiss. Okay, so this is the solution of the Laplace equation on the mesh. This is the first iteration, the second iteration, the third, and so on and so forth. So you see how it changes with every iteration. Okay, so I mean, in particular, if you look at it carefully, you will see that it relaxes a little bit, right? That makes sense. So if you think about the solution of the minimal surface equation as something that solves, well, a minimum surface, this one here looks a little bit too stiff and it relaxes, right? This is what our eye says should happen if you want to find the solution of the minimal surface equation. So the eye is actually pretty good at this. So I would say with this, we've successfully managed in 30 minutes to create a program that solves the minimal surface equation. And you saw that if you have something that solves the Laplace equation, it's actually quite simple to do this. There is not very much that needs to be done. And so with this, I'll leave it. In the next lecture, I will show you how we solve that equation if you wanted to use a third different method, namely a pseudo time stepping approach.